The second law introduced here is Kepler's second law, which can be summarized as gravitational bodies rotate through equal areas in equal time. In this case, a line drawn from Earth to Sun sweeps the same area of the orbital plane every day, regardless of where the planet is in its orbit. Consequently, Earth moves faster when it's near the Sun than when it is far, because at the smaller distance it needs to trace a greater arc to cover the same area. This means that Earth spends less time close to the Sun. Third and last is the inverse square law. It treats the Sun as a point source of light that distributes energy evenly in all directions. Therefore, at a given distance from the Sun, its energy is distributed over a surface area of a sphere, 4 pi r squared. At twice the distance, its energy is distributed over 4 times the area, and so on. The inverse square law states that the amount of energy striking an area decreases with the square of the distance from the Sun, or in mathematical terms, I equals I sub 0 over 4 pi r squared, where I equals the solar energy per unit area, I sub 0 equals the initial solar energy, pi equals 3.14159, r equals the distance from the Sun. The distance between the Sun and the Earth varies between 147 million kilometers on January 3rd and 152 million kilometers on July 4th. Putting these values into this equation means that Earth, at its furthest distance from the Sun during the summer in the Northern Hemisphere, receives only 93.5% of the solar energy that it receives at its closest distance. Nonetheless, the more acute angle of the Northern Hemisphere to the Sun during July more than compensates for the further distance. For example, at the Tropic of Cancer, the ratio of solar energy in June over solar energy in December equals I sub 0 cosine 0 degrees over I sub 0 cosine 46.8 degrees, or 146%. Together with the effect of distance, this equals 93.5% and 146%, which equals, in total, 128% change. As discussed above, Earth's diurnal axis of rotation currently has an angle of 23.4 degrees with respect to its orbital plane around the Sun. The planet, however, wobbles like a spinning top, and this angle oscillates between 22.1 degree and 24.5 degrees every 41,000 years. This means that the seasonal difference in the amount of solar energy reaching Earth varies with a period of 41,000 years. At the extremes, the current Tropic of Cancer, latitude 23.4 degrees, would receive 142.6 or 149.1%, about a 4.5% change in solar energy from the minimum to maximum tilt. The elliptical shape of Earth's orbit around the Sun is characterized by its eccentricity. Eccentricity in mathematical terms is E equals A minus P over A plus P, where E is the eccentricity, A is the aphelion, farthest distance from the Sun, P is the perihelion, closest distance to the Sun. Currently, Earth's orbit has an eccentricity of 0.0167, but it oscillates between 0.005, nearly circular, and 0.0617, more elliptical, with an average periodicity of about 100,000 years. As the eccentricity of Earth's orbit increases, the amount of solar energy reaching Earth fluctuates more from summer to winter because of the greater seasonal differences both in the distance between Earth and the Sun, inverse square law, and the time spent at the aphelion and perihelion, Kepler's second law. When the eccentricity is near circular, seasonal variation derives solely from the differences in the angle between the axis of Earth's diurnal rotation and its orbital plane around the Sun, cosine law. At present, the summer and winter solstices and the aphelion to perihelion, furthest to closest, nearly coincide. The solstices are June 21st and December 21st, while the aphelion and perihelion are respectively July 4th and January 3rd. Earth, however, behaves like a wobbling top, and the alignment of the axis of Earth's diurnal rotation with distance from the Sun oscillates with an average period of 21,000 years. That is, 10,500 years ago, Earth was closest to the Sun on July 4th, when the Northern Hemisphere was tilted toward the Sun, and furthest from the Sun on January 3rd, when the Northern Hemisphere was tilted away.